In this tutorial, we're going to discuss vertical curves and what the criteria is for vertical curves, as well as how you enter and what you look at, the inputs and outputs in Sidewinder. We're actually going to break this into two tutorials. The first is going to be more of just the bare bones basics, and the second one's going to be a bit more advanced. So again, I've opened our tutorial example, have modified it slightly. We're going to just pick just the full and empty case, just to keep things simple for right now. If we go to our geometry, again, you can refer back to the profile tutorials earlier in this series, but I just want to point out again that the radius for each curve is entered on the element at the start of the element. In other words, if we look at this convex curve here, that's going to be entered at this point. If we go to the next one here, that's entered right there as the start of it. Now by default, if you leave the curves blank, Sidewinder will not do the curve calculations at all. If the element, even though there's a change in slope between these two elements, Sidewinder won't do the calculations unless you enter at least something, a value for that curve. So just as a starting point, I'm going to go ahead and just simply enter 50 meters in each curve. And we can see we've got two convex curves and two concave curves. Now to start out, before we run the calculations, let's just discuss what's important in the convex curve. Well, in the convex curve, we've essentially got two criteria we're trying to meet. One is overstressing the edges of the belt. Since we're bending this around a convex curve, we stress the edges, and therefore we need to keep those stresses within an allowable region. The second criteria for convex curve is buckling of the center. Since we've got some neutral axis, and Sidewinder will automatically calculate the neutral axis of the belt based off of the troughing angle and the belt geometry and so on and so forth. But we've got our neutral axis, and when we bend that, we're going to reduce the stresses in the center of the belt and increase the stresses at the edge. So in this case, the edge stresses, and if we go back to our design criteria for a second here, we can see that on this conveyor we've got a steel cord belt, and our edge stresses we're going to allow 10% higher on the edges. During starting and stopping, we're also going to allow an additional 15% higher stresses during the starting and stopping cases. In the center of the belt, the minimum stress always has to stay positive in a convex curve. Now when we talk about a concave curve, we've essentially got just the opposite. We're increasing the stresses on the center, and we're reducing the stresses on the edge. Now the edge of the belt actually, SEMA allows for what it calls a control buckling, and sort of the idea here is it allows some, you can actually have negative stresses at the edge of the belt, and the idea is basically that the belt won't really buckle, it will simply bow out a little bit. So SEMA does allow for a small amount of compression in concave curves at the edge of the belt. The center of the belt in a convex curve, it's never allowed to go below zero. Other main criteria with the concave curve is obviously liftoff. So if we look at our belt tensions and we look at what the belt mass is, we can calculate whether the belt is going to lift off, and that's obviously not acceptable. And in fact, Sidewinder will look at two criteria. It'll look at what the liftoff criteria is for the fully loaded or the full nominal belt mass, and it'll always also look at the calculations for the worn belt mass. Obviously, if you've got a given tension, be it 10 kilonewtons, the belt's going to lift off. You're going to have a more stringent requirement if your belt mass is reduced. So that worn belt mass case is typically your governing design condition. We'll talk about that more in the advanced calculations. But for now, we've simply entered 50 for each of our radiuses. I'm going to go ahead and hit the Run button. And if we now look at our output and go to our vertical curve page, there we go. We can see we've got some red, we've got some problem here. And just to discuss this page just quickly, the light colored elements are our carry side, and our dark is just the mirrored return side. So we can see that obviously this is our first convex, and we've got a convex return mirror image of that. That's our second one. There's the return side, equivalent return, third, and there's our last convex curve. The next column here is just what the current radius is. A positive value in Sidewinder by definition is a convex curve. A negative is a concave curve. Now when we enter it in the geometry page here, we always just enter a positive value simply because Sidewinder, based on the geometry, is going to know whether that's a concave or convex. But when you have tables like this that it's not obvious which it is, we simply use the convention of positive being a convex and negative being a concave. Required radius. Now this looks at all our different cases, and we notice when we hit the vertical curve output button here, we have the all tab as well as each of the individual cases. So I could go ahead and say, what's my requirement for just the fully loaded normal case? There it is. What is it for empty? Or all just takes the worst condition of all of these. So we can see for steady state running in the all condition, we need a radius of 104. The required for dynamic conditions is 109. That actually occurs during starting. The reason is for stresses on the belt, and it's actually in the empty case. So if I look at the empty case here, I can see, there's my 109. That's the governing condition. Fully loaded, it was actually 97. So we need 109 for this first convex curve. I can go back to our geometry and say, all right, we needed 109. Let's put in 120. Give ourselves a little bit extra there. So now I can go back to the main page. My next curve needs to be 290 for running. I need 531 for all my dynamic. Again, starting, and this is lifting off the belt. Lift off, worn belt condition, starting the empty belt. So when we start up the empty belt under the worn friction condition, we actually need a radius of 531 to keep the belt from lifting out of the curve. Again, I could go back to my geometry and say, all right, let's change this to say 550 or whatever. I'm going to show you a little shortcut, and that's this information down here. When I click on each of these curves, we can see there's some information that's changing. For example, when I click on this one, I can see, hey, I could just quickly select a radius of 300 or 550 is my worst case dynamic. Geometric just means that's the biggest radius I can physically fit in the curve without adjusting that element, i.e. changing my IP point or something like that. With my current two elements, that's the biggest I could get. And I could also just manually enter a value here. And what this allows me to do, if I hit update, so I'm on this flight, I'm going to hit update, and it just simply updated that radius to 550. So rather than me having to switch back and forth between these two pages, there it is right there, 550. Rather than me having to switch back and forth and remember what it is, I can just enter the value right here. So for example, this third concave curve, or the third curve we've got, it requires 625. I'm just going to enter 632 and hit update just to show you. 632, I go over to my geometry. Hey, there's the 632. So it's just a little shortcut. And my last one here, we need 225. Hit that. Now you have to remember, after we've adjusted these radii, when I rerun my calculations, those radii might change just slightly because we've physically changed the geometry of the conveyor. Since we've changed the geometry, our tensions there therefore might change a little bit, and sometimes it might take a couple iterations to sort of narrow in on those final requirements. So I might go back up here and, okay, let's just step through this again. And it's literally as simple as that. I can go through and just click on each one of those, say update, hit run, there we go. And now we can look and see that for this particular conveyor, everything seems to be working just fine. Now, it's important to remember, and we discussed this in some of our other tutorials, that just looking at the empty and the fully loaded case for this conveyor very well may not be the worst case condition. We might need to go back to our input, and let's look at this incline case and this decline case. Again, here's our incline case, inclines and flats, and here's our decline case. So we very well might have to also include those. So we're just going to rerun the calculations with those cases, and we can see, hey, now we need 136, we need 725, we need 779, it's going to round to 800, and we need 525. So I could, of course, just say update, 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 and run, and hey, now all's well. And there we go, we're basically done again. Now, as engineers, we should also go back and look at this and say, all right, for steady state running, for example, this convex curve here, we only needed 164 for steady state running, but we actually had to put a 525 due to starting. Well, this might be a time that we look at our design and say, well, hey, can we reduce our starting tensions, or maybe we need to increase our belt rating? I mean, that's a pretty large convex curve requirement there. Same with our concaves for liftoff. We've got 359 and 373, but we're requiring 705 and 783 for starting. Well, what's going on with this conveyor during starting? If I go back to my for example, fully loaded case, I can see I'm starting the conveyor in 15 seconds. Again, this is discussed more on the motor and the dynamic tutorials, but we can go in here and let's, for example, pick a variable frequency drive, and let's increase that starting time from 15 seconds to maybe 25 seconds. When I rerun the calculations, that will obviously reduce my belt stresses. I can now go back to my vertical curves and say, hey, look at that. Now I'm down to 417 and 518. Remember, that was like 700 and 780 or whatever it was. And down to 290 for my convex curve. So that's helped drastically reduce these curve requirements. Here again, I'll select the first one. Rather than manually going over and rechanging all these curves, I'll simply say update, 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 update. Go back and just check. Sure enough, they're all updated. Hit run, and there we go. So that's it in a nutshell for the vertical curves and how you work with it. Again, in general, in a convex curves, you're worried about maximum stress in the edges, and in a concave curve, you're worried about belt liftoff. But Sidewinder looks at all the requirements and simply lets you know what the reason was and which case it happened on. You can see these are happening on the incline full case. This curve was actually being designed off the decline low friction case. It's pretty powerful, and that's it.